Hey guys, welcome back to STR8CHEM. In this video, we look at the two anomalous cases for electronic configuration. But before we look at those cases, it's better for us to get to know what does it mean by anomalous. Anomalous is defined as deviating or being different from what is expected. We have two cases for the anomalous electronic configuration. In Chapter 2, Atomic Structure, we're going to look at chromium and copper. Do you remember, everyone? These are the only two anomalous cases in Chapter 2. You do not have any other anomalous cases. Therefore, this one should be easy for you to understand. Okay, I repeat, these are the only two anomalous cases in Chapter 2, Atomic Structure. First, we're going to look at the anomalous case number 1, which is chromium. We do know that the proton number for chromium is 24. The expected electronic configuration will be written as this: 1s2, 2s2, 2p6, that is 10. 3s2, 3p6, 4s2, 20, and 24. Remember, in the previous video, I've told you when you start filling in 3D, you need to switch places between 4s and 3D. And that will only happen between 4s and 3D. Please remember that very well. Now, this is expected configuration based on, okay, this expected electronic configuration is based on the Aufbau principle, okay, expected from Aufbau. But the actual electronic configuration, now you can see that we have changed to actual. This one is expected. And now you have the actual. The actual will be different. You have 3D5, 4S1. So that is what is happening here. In the expected electronic configuration, you have 3D4, 4S2. In exams, when they ask you to explain about an anomalous case, you need to write the expected first. So when you write this expected electronic configuration, they're going to give you 1 mark. And then you need to write the actual electronic configuration. Again, I repeat, this comparison between expected and actual will only happen between chromium and copper, but not anything else in Chapter 2. We only have two anomalous cases. So the thing that will be different over here is this. You have 3D5, 4S1. When you converted that to orbital diagram, so these are the orbital diagram, you can see that this is, when you look at here, that is half fill 3D. Okay? You have half fill 3D right there. So when you write the actual electronic configuration, so this is the actual electronic configuration, you get another 1 mark. Okay? 1 mark for the expected based on Aufbau. And then you have the actual electronic configuration. You have another 1 mark. And you need to explain why does the electron, okay, one of the electrons from here transferred to the other side to make it 3D5. Because in the beginning, when you look in this, you have 4s2, 3d4. And how do you get that to be a 3d5? The electrons from here, one of them will be transferred to 3d to have the actual electronic configuration. Why is that so? Because of the stability of half-fill orbital arrangement. Since the 4s and 3d energies are very close, one of the electrons from 4s2 orbital is able to jump to fill the partially filled orbital of 3d4 orbitals to produce 3d5 4s1. So in other words, you can write half fill 3d orbital is more stable than partially filled 3D orbitals. Okay, so when you write that, you get 1 mark. Okay, try to remember this sentences as well. So what does it mean by half filled? So you've seen that just now. Okay, so this is the half filled. These are the partially filled. Okay, so if you take that out, 1, 2, 3, 4, 5, 3D, you get 1, 2, 3, 4. So this is partially filled 3D. Okay, so it is less stable than half filled 3D orbitals. So that is for chromium. What about copper? Copper, the expected electronic configuration, you will have 3D9 4s2. Okay, 3D9 4s2. So when they want you to explain about the anomalous case, remember, you need to write this first. You get 1 mark. And this one is based on, expected based on Aufbau principle. And moving on to the actual, when you write the actual over here, you get 1 mark. Why is it going to be like this? Again, you have the one of the electrons from 4s will jump into the 3D. So look at the red one. So this is the actual electronic configuration. Then you get this. So that is the fully filled 3D orbitals. Okay. So again, the stability is due to the fully filled orbital arrangement. So it's the same as what is going on over here. We'll jump into the partially filled orbital of 3D9 orbitals to produce 3D10 and 4s1. So in other words, you can write fully filled 3D orbital is more stable than partially filled 3D orbital. Again, by writing that, you should be able to get another 1 mark. And you need to remember this as well, okay? So those are the anomalous cases in chapter 2, atomic structure. Remember, only for chromium and copper.